Let's go over architecture pruning, quantization, sparsity, and perplexity. These should be considered when choosing high-speed data transfer protocols. Pruning systematically removes less important parts of a neural network to make it smaller and faster. There's almost always a trade-off between space and time when considering information encoding. Sparsity refers to the percentage of model parameters, or weights, that have been removed or reset to 0. A model with 50% sparsity means half of its original weights have been pruned away. Perplexity is a primary metric for evaluating language models. In simple terms, it measures how surprised or confused a model is by a sequence of text. A lower perplexity score indicates that the model was better at predicting the sample text. Quantization is the process of reducing the precision of the numbers used to represent a model's weights. Think of it like this. A high-precision number is like having a ruler with millimeter markings, while a low-precision number is like having a ruler that only shows whole centimeters. You lose some fine detail, but the number is much simpler to write down and work with. Typical training occurs at 32-bit or 16-bit floating point numbers, which can represent a large range of values with high precision. Quantization of these numbers into smaller data types like 8-bit or 4-bit integers involves steps of scaling or rounding. Scaling involves reducing the high-precision value to a smaller range of integer values, where rounding takes each high-precision weight and rounds it to the nearest available integer in a new smaller range. This drastically shrinks memory usage and speeds up calculations. Here, a perplexity score versus total model memory weight compares different quantization methods on Llama 2 with 7 billion parameters. The ideal score is the lower left, where memory and perplexity are both low. 4-bit quantization seems to be the most efficient. There is a noticeable increase in perplexity as 3-bit quantization is performed. Let's go into common protocol comparisons. Here we will compare different compression methods and inference engines. The WandASP pruning method prunes by weights and activations. GPTQ 4-bit quantization. Activation-aware weight 4-bit quantization. OmniQuantization uses learnable weight clipping. TensorRT is an engine that optimizes multi-GPU processing. VLLM is a high-throughput and memory-efficient inference and serving engine for increasing LLM efficiency. For a more interactive tutorial, check out the GitHub link. You can copy and paste the code into Gemini and interact in creative ways to modify the tutorial to your needs. Be sure to check out other free tutorials in the open-source library.